Okay, so good morning, everyone, to the third and final day of this wonderful conference. So today, the first talk is by Professor Seiichi Kamada from Osaka University. He will be speaking on braid presentation of twisted links and spatial graphs. So, Professor Kamada, please.
Yes, thank you. So today, I'd like to talk about braid presentation of twisted links and also spatial graphs. So here is the contents of my talk. First three braid presentation of twisted links. This part is joint work. This part is joint work with Prabhakar and Negi. And after that, I'd like to move to Alex braid presentation of spatial graphs. And this part is the part on spatial graphs is a joint work with Victoria Lebedge. So two different topics. And here is a definition of virtual links, but maybe we don't need to recall the definition of virtual links. Anyway, a virtual link is an equivalence class of virtual link diagrams by these moves R1, R2, R3, and V1, V2, V3, V4. And the twisted link is not so familiar. A twisted link diagram is a link diagram, possibly with virtual crossings and bars. Bar is like this. And the twisted link is the equivalence class of such diagrams and equivalence relation generated by these moves. So first R1, R2, R3, V1 to V4 are Reidemeister moves for virtual links. And additionally, we consider three moves T1, T2, and T3. Such an equivalence class is a twisted link. This notion was introduced in Vaughan's paper, in this paper. So by definition, the virtual links classical links are subset of virtual link diagrams. And the virtual link diagrams are subset of twisted link diagrams. And the equivalence relation, classical links correspond to link diagrams modulo this relation generated by Reidemeister moves. So this equality is Reidemeister theorem. And the virtual link is, by definition, it is an equivalence class of diagrams by this equation, this relation. And the twisted link is, by definition, it is this one, twisted link diagrams modulo this equivalence relation, T, twisted link. So obviously, if two diagrams are equivalent as classical link, then they are equivalent as virtual link. And if two diagrams are equivalent as virtual link, then they are equivalent as twisted links. So we have a natural map from the set of links to virtual links and virtual links to twisted links. It is known that the map from the set of links to virtual links, this map is injective. So in this sense, a virtual link is a generalization of a classical link. And also, the map from the set of links to twisted links is injective. But however, the map from the set of virtual links to twisted links, this is not injective. So, but it is known when two virtual links are equivalent as twisted links in these papers. So this is a relationship between virtual link and twisted links and classical links. Another aspect, virtual links correspond to stable equivalence classes of links in second-oriented surfaces. And on the other hand, twisted links correspond to stable equivalence classes of links in second surfaces. So anyway, virtual links and twisted links are defined using diagrams, but it has actual geometric meaning. These are references. Now we discuss about the braid presentation of twisted links. So before that, we need to introduce twisted virtual braids. Twisted virtual braids. Twisted virtual braid diagram is a diagram of a braid, possibly with virtual crossing and some bars. This is a twisted virtual braid diagram of degree 3. And two such diagrams are equivalent if they are related by a finite sequence of ambient isotopies and extended Reidemeister moves. But this is important, keeping the condition of twisted virtual braid diagram. The twisted twisted virtual braid is equivalence class of twisted virtual braid diagrams. The set of twisted virtual braid of degree n forms a group, like braid group. That is called twisted virtual braid group. And in this talk, it is denoted by TVBN, twisted virtual braid group of degree n. And sigma I is a standard generator for classical braid, and VI is a generator corresponding to virtual crossing. And gamma I is a generator which has one single bar on the I strand. These are standard generator for the twisted virtual braid group. And as you know, R2 move corresponds to these moves, these braid moves, and R3 move correspond to this kind of moves. And virtual V2, virtual Reidemeister move correspond to this move, and V3 correspond to this one, and V4 correspond to these moves. Okay. And T1, T2, and T3. T1 correspond to this braid move. Also, this is also T1, and this is T2. And I'm sorry, I forgot to draw the picture of T3. T3 is this one. So if we look at this figure this way, then the figure becomes like a braid form. That is T3 move for braid, twisted virtual braid. So anyway, using standard generators, we have these relations. And actually, these are defining relations for the twisted virtual braid group. The twisted virtual braid group is generated by standard generators and defined using these relations. Now, we we consider braid presentation for twisted links. First, Alexander theorem for twisted links. Every twisted link is represented by the closure of a twisted virtual braid diagram. So here is a twisted virtual braid diagram and taking closure. Okay. So any twisted link is represented in this form. This is Alexander theorem. And Markov theorem, we introduce three kinds of moves. So first move is TM1 move. TM1 move means a twisted Markov move of type 1. That is easy. B1, B2 element of twisted virtual braid group. Then replace B1, B2 with B2, B1. And we say that B2 inverse B1, B2 is obtained from B1 by a conjugation. And our conjugation is the same with a TM1 move. So our conjugation may be also referred to as a TM1 move. Sometimes TM1 move is defined in this way, or sometimes it is defined by a conjugation. It is essentially the same. And second move, TM2 move, twisted Markov move of type 2, or this is called stabilization. Stabilization of positive type or negative type or virtual type. That is a replacement of a braid like this. This is the first braid, B of degree n. Then we add one strand on the right, and we put a sigma m standard generator, or negative one, or virtual one. These are called stabilization, positive type, negative type, and virtual type. And when we consider closures, then it's easy. The closures, the equivalence class as twisted link is preserved by these moves. This is a natural generalization of classical Markov theorem. And we also introduce third kind of moves, TM3 move, or twisted Markov move of type 3. It is also called a right or left virtual exchange move. That is a replacement of this one. This is right virtual exchange move. Here is B1, B2 any braid, and this is a negative standard generator and positive standard generator. Replace these crossings by virtual crossings. This is virtual exchange move. And so similarly, but we put the strand on the left side. In this case, we call a left virtual exchange move. So these two moves are TM3 move. And this is a theorem corresponding to Markov theorem for twisted links. Two twisted virtual braids have equivalent closures as twisted links if and only if they are related by a finite sequence of twisted Markov moves. So TM1 move, TM2 move, and TM3 moves, and their inverse operations. This is a Markov theorem for twisted links. And here is a remark. Left TM3 move, there are two kinds of TM3 move, left and right. A left virtual exchange move is equivalent to a right virtual exchange move up to TM1, up to conjugation. So we may remove left or right from the definition. So we don't need one of these moves for this Markov theorem. And another remark, it is known Markov theorem for virtual rings. It is in my paper in 2007. So our Markov theorem for virtual rings was introduced in this paper, and our twisted Markov move of type 1, type 2, type 3 correspond to a virtual Markov move of type 1, type 2, type 3. They are corresponding. And another remark, another Markov theorem for virtual rings is given by Kaufman and Lamborghini in this paper. And their Markov move is different from our moves. So this is a braid presentation for twisted rings. Now, and these are joint work with Prabhakar and Negi. Is any question for now? Then let me move to the next talk, braid presentation with spatial graphs.
Oh, Seiichi, excuse me.
Oh, yes.
Can I
Yes.
ask, is it possible to define some analog of the pure twisted virtual braid group? Because it's important in the classical case for the virtual and for twisted virtual. Did you define the pure twisted virtual braid group and studied its structure?
Yes, we can define pure twisted virtual braid group. And I have not studied yet, but Prabhakar maybe. Prabhakar, do you hear me?
Yes. In fact, we are doing that work. Yes, it is possible to define pure virtual braid, pure virtual twisted braid. Yeah.
Yes. And can you say something about the structure of this group? For example, solution for the word problem, some decomposition into semi-direct product, or you have only definition?
As of now, we defined the definition. We are working into it. We did not go into the details.
Okay, thank you. Is it possible to find your text in archive? Maybe.
Sure.
Okay, thank you.
Okay, thank you. Oh, and our theorem with Prabhakar and Negi, this result is on between a preprint and which is on archive a few weeks ago. So you can see the details for braid presentation for twisted rings. Okay, now we discuss spatial graphs, braid presentation of spatial graphs in 3 space. So in this talk, graph means a finite directed graph. So each edge has an orientation. And when I say inessential vertex, means a degree 2 vertex with one head and one tail. So this is an inessential vertex. Usually we ignore inessential vertex. Now, a spatial graph is a graph embedded in R3 or S3. 2 spatial graphs are said to be equivalent if they are ambient isotopic, after adding or removing some inessential vertices. So when we discuss a spatial graph in not theoretical point of view, we ignore the differences of inessential vertices. This assumption is not so important, but convenient. Here is Leidmeister moves for spatial graph diagrams. So we can we can draw spatial graphs by diagrams. And these are Reidemeister moves. So first three are classical Reidemeister moves, and this one is a Reidemeister move for spatial graph. And this one, two adjacent edges, we can twist between two edges like this, positive direction or negative direction. Twist. These are Reidemeister moves. Now, okay, and we need to define a graph braid. Graph braid of boundary type Mn is a graph G embedded in the cylinder. Here's M and N are non-negative integers. And it satisfies these two conditions. The restriction map of the projection to the second factor to each edge is an orientation preserving embedding. So here is an example of a graph braid. If please look at one edge, and the restriction of the projection to this edge is an orientation preserving embedding. So every edge, it is embedded orientation preservingly, and the boundary, this part is intersection of the G and the boundary of the cylinder is xm cross 0. Xm is a fixed m points on the two disks, lying on a straight line. This is x4, 4 points, and this is x3, 3 points. So this figure is an example of a graph braid of boundary type 4-3, 4 points to 3 points. And if the boundary type is mm, the same number, then we can consider closure as usual. This is a closure. And Alexander's theorem, this is Alexander's theorem. For any spatial graph G, there exists a graph braid B, such that G is equivalent to the closure of B. As this is Alexander's theorem. Now we can discuss Markov theorem. We introduce three kinds of moves as Markov theorem. M1 move or conjugation. This is the same. B prime, and we replace B prime and B. This is first Markov move of type 1. And the Markov move of type 2 or stabilization. This is also the same with the classical case. Positive stabilization and negative stabilization. Add one additional arc strand and put a standard generator. This is stabilization. And additionally, we need a third kind of move for graph braid, M3 move or graph braid stabilization of negative type or positive type. This is original braid, and add one extra strand here, and here is a positive crossing, and here is two negative crossing. This is negative type stabilization. And similarly, we add one additional strand and negative crossing and two positive crossings. This is a positive type graph braid stabilization. And this is a theorem, a Markov theorem for spatial graph. This is announced in extended Cook seminar in 2015. But paper is not published. Actually, we write a preprint, but now I'm updating the preprint again. So after that, I'm going to put on archive. let G be a special graph. If two graph braids B and B prime have closures equivalent to G, then they are related by a finite sequence of M moves, conjugations, stabilizations, and graph braid stabilization, and inverse operations. This is Markov theorem.
আপনি কি করবি?
Any question?
জেল থেকে পালানো।
Okay. So let me
Yeah. Hello?
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 Yes. Okay. Let me explain about graph braid stabilization. This is important and it is not so familiar. So here is a vertex.
No, please go.
Here is vertex of vertex type. Degree type means in the pair
Go ahead.
of
I mean, it was some internet issue here, so the screen was stuck, I suppose.
in degree and out degree. This vertex is four incoming edges and 3 outgoing edge. So this is the vertex of degree 4, 3. Okay? And M3 move of degree PQ means M3 move, and this vertex is type PQ. For example, this move is a graph braid stabilization of degree type 4, 3. 4 incoming and 3 outgoing. Yeah. Degree type 4, 3. And maybe I will skip the details. So if we look at the vertex, and if we move a graph braid by isotopy, then around this vertex V, the endpoints is moving on the small ball. And in this picture, A1 to AP on the incoming edges, and these points are outgoing edges. So after moving, and after coming back to the same position, then we have a permutation of these points A1 to AP, and the permutation of these points on the sphere. That is called motion braid at V. So if we have an ambient isotopy keeping the position V, then we have a motion braid around this vertex. And
sorry, so it means that your vertices are not rigid, yes?
Not rigid, yeah, not rigid case, yeah, you're right, not rigid case. And such a braid is generated by a standard generator sigma I around this, and the standard generator sigma I around this. But for this part, sigma I square, that is generators for such a braid. Okay? So this type of braid, but I is not equal P, and or sigma P square or sigma P negative square. Okay. So, and if it's sigma I case, then that is these moves. Okay. These moves, I is smaller than P, then these moves. And if I is bigger than P, and these moves. And these moves are just graph braid equivalence. We consider these same braid. But this case is a problem. Yeah? This twist, sigma P square. And in this case, moving isotopy in R3, we can move like this. So please consider the closures. Then this is isotopic move. They represent the same twist, same spatial graph in R3. And this is negative graph stabilization. So graph stabilization occurs if we have such a twist. In this case, we need this move. And here is the remark. If M3 move is type 0Q, 0Q means there is no arcs above the vertex. In this case, we consider it is identity transformation. Or P0, there is no strands below the vertex. Or type 1,1. Type 1,1 is like this. 1H and 1H. These are usual Markov move, usual M2 move. And Victoria and I proved if PQ is 1, 2 or 2, 3, then such a M3 move is reduced to M1 move and M2 move. So we don't need M3 move. Here is a proof. If we have a 2-1 type, this is 2-1 type vertex, and up to isotopy, we move this braid like this, and apply a M2 move, and braid equivalence. And also, this is also a braid isotopy. And from this one to this one is M3 move of degree type 2-1. And similarly, a negative type, it is a little complicated, but anyway, 1, 2, degree type 1, 2, and from here to from here to this one is M3 move, graph braid stabilization, but it is realized by equivalence and M1 and M2 moves. So we can say this, let G be a spatial graph such that the degree of each vertex is less than or equal to 3. Then we don't need M3 move. So if two graph braids B and B prime have closures equivalent to G, then they are related by a finite sequence of conjugation and stabilizations, and their inverse operations. We don't need graph braid stabilizations. And this we announced this theorem, but this time we improve a little. Theorem 5.6 is a little refinement, stronger than 5.5. Let G be a special graph such that for each vertex, the in degree or out degree is less 2. If two graph braids B and B prime have closures equivalent to G, then they are related by a finite sequence of conjugation stabilization and their inverse operation. We don't need graph braid stabilization. And maybe let me skip this one. I don't have much time. But anyway, here is a lemma. And I think I have 5 more minutes.
Yes, it seems.
So let me tell about the special graph with rigid vertices. Rigid vertices. Special graph, a vertex V of a special graph G is called rigid vertex if there is a flat 2 disk. Flat 2 disk with the center is V, okay, such that the intersection of G and the disk is intersection of B and G. Here, B is a 3-ball neighborhood of B. In this case, this 2 disk is a supporting disk. And a special graph with rigid vertices is a special graph whose vertices are rigid vertices. So each vertex has a 2 disk, flat 2 disk, and H is on the disk. And two such graphs are equivalent as a special graph with rigid vertices if they are equivalent by isotopy of R3, carrying supporting disks of vertices of G to those of G. So here is a Reidemeister move for spatial graph diagram with rigid vertices. So the difference is this move. So not rigid case, two adjacent edges we can move like this. But rigid case we cannot do this. But just flip the disk. It is such a move is allowed. And in this case, Alexander and Markov theorem. Alexander theorem is, as usual, for any spatial graph G with rigid vertices, there exists a graph braid with rigid vertices such that G is equivalent to the closure of B. And Markov theorem is similar, but the difference is we don't need graph braid stabilization, just conjugation and stabilization. So we don't need graph braid stabilization in rigid vertex case. So maybe Andrei's question is on this one. So rigid case and unrigid case is different statement. Yeah, that's all my talk. Thank you for your attention.
Yeah, thank you very much. Seiichi, can I ask a question?
Yes.
Of course, you know there are nice polynomial invariants for spatial graphs. For example, Yamada polynomial, Yoshimada polynomial.
Oh, I see.
Did you try to obtain something using your approach?
Actually, Yamada polynomial, not yet. So I just by counter and bicounter using for spatial graph or twisted links, counter is defined. And using graph presentation, the computation is easier. That is one merit. But I don't have a new invariant yet. And I haven't tried Yamada polynomial using this braid yet.
Okay, thank you.
Okay. So Professor Kamada, there was also a question from Mahinder in the chat box. But unfortunately, my internet went away and I cannot see that message in the chat box. So, Mahinder, can you please ask the question again?
Yes. What is the obstruction for virtual links to equivalent as twist links? What is the obstruction for virtual links to be equivalent as twisted links? Maybe the question is about my first paper.
Yeah, it's regarding failure of injectivity.
Yes. This one.
Yeah. Yes.
Yes. Okay. For one component case, so virtual node. Okay, one component, virtual node. If we have two virtual nodes, K and K prime, they are equivalent and twisted link. If and only if K is equivalent to K prime as virtual node, or K is equivalent to the virtual dual of K prime. And the virtual dual means first considering reflection image by a straight line on the plane. So we have a diagram and put a straight line and take a mirror image. Take mirror image by this straight line. And after that, taking all positive and negative crossing changes. So first to make a mirror image, and then we have also another mirror image changing positive and negative. So that is I call the virtual dual. And the classical node case, taking mirror image and mirror image. So that is the same node, same classical node. But the virtual node, this mirror image and another mirror image is different in general.
Yeah, sure.
And that is the only case two different virtual node becomes the same twisted node. In the multi-component case, similar, a little different, but similar. So details is in this paper.
Okay, thank you. And you said you have defined some quandle analog for twisted links. So is it the usual quandle together with some additional structure? And
yes,
what is
yes.
that structure?
Yes, yeah, you are right. You are right. Actually, I defined a condition of additional structure. So there are many extensions. So I call the T structure. T structure is so bicandle with T structure is an invariant of twisted link, and there are you can find many different T structures.
Okay, thank you very much.
Seiichi, is it possible to define some analog of quantal for a spatial graph? Because I remember that Mohammed defined some sync quantal for singular nodes. But for spatial graph, for arbitrary vertices, is it possible to define some analog of quantal?
Yeah, in my idea, not my idea. Maybe it's folklore for graph, spatial graph case, oriented, edges are oriented,
Yes.
spatial graph case, and it is more natural is removing the vertices, neighborhood of vertex. So
Yes.
the vertex 3 ball remove in S3. So you have a compact 3 manifold.
Yes.
And proper oriented embedded arcs. In that case, we can define quandle without no restriction. And
But I know the definition for if we have a spatial graph where all vertices have the valence free, then it's possible to define with some analog of quantal. But in general case, I don't know the papers in this direction. Do you know something?
No. It's okay, well defined. So in general, fundamental quandle is defined on compact oriented 3 manifold. And inside there is oriented to 1 manifold, proper 1 manifold. In that case, quandle is well defined.
Really?
Yes.
Okay, thank you. I'm asking you. Okay.
Excuse me. Could you say if there is a compact, manageable, two-dimensional generalization of the theory of spatial graphs?
Pardon?
Two-dimensional version of linearizable surfaces of something like this.
Two-dimensional visor.
Two-dimensional, yes. Yes.
Oh, I see.
So the discrete version of two nodes of something like this.
Yes. So one.
A priori, it's difficult, but do you know if there are some approaches to this?
Yes. Scott Carter, and also I'm joining, but the notion of form is too complex, and embedding forms in form manifold. That is maybe generalization of trivalent graph.
Thank you.
Okay, so any more questions? Okay, so if there is no more questions, let's thank the speaker.
Thank you.
Yeah, thank you, Professor Kamada.